So today we're going to shift gears a little bit. We've been talking about finding internal forces in these big truss structures and other things. Big assumption we made were that the forces were essentially two force members. So each member had only pure tension or pure compression. So only two forces acting in the exact same line, either pulling out or pushing in either direction. So we had the few assumptions, things like the forces were only applied at the joints. So the question is, what happens when they're not only applied at the joints? So in that case, we'll end up with not two force members, but something called multi-force members. And those multi-force members then goes into today's topic, which is frames and machines. So before we get there, need to deal with multi-force members. So any member that's not in pure tension or pure compression is called a multi-force member. So it can have some component of force acting perpendicular to its axis. So not just pure tension or compression. So usually when this happens, the member is going to be bent a little bit. So if I have a member and I push it right in the middle, it's going to end up bending that member. The amount of bending is not important yet. That's going to be important in one of your next classes, CEE 220, Mechanics of Materials. So in that class, you'll be able to figure out actually how much things are going to bend. But the first step in that is doing a statics analysis to find out what those internal forces inside of it are. And so kind of first step in that is this multi-force analysis that we'll be doing today. And so here I have an example where I have this structure connected by pins. So there's pins at B, C, and D. That's what the little circles represent. It's also technically pin connected at A and D. Those ones aren't that important though. And then again here, instead of having my forces act just at the joints, these forces are acting at other locations. So this force F pushing this member here to the right, that's going to kind of cause it to bend a little bit. So from point C, it's going to kind of be bent out this way. Same thing, point or force P over here, pushing this guy down. It's going to kind of bend this guy downwards. And so one thing I want to emphasize here is that even though I'm talking about, this force bending this member and that force bending that member, in terms of our statics analysis, we're still dealing with purely rigid bodies. So even though I'm saying that this is going to want to bend this thing, I'm still assuming that these things are completely rigid. These things are not going to bend. So again, the actual bending will be one of your future classes. For now, we're still assuming everything's rigid and nothing is actually bending. But what we're concerned about now is the fact that these are now multi-force members. And so we want to know what those forces are inside of them. So the forces in these members are not in pure tension or pure compression. So the force in this member does not lie along its axis because again, this force here is going to try to make it bend a little bit. So it'll be a kind of transverse force to that normal or axial force that acts along the beam itself. So basic procedure when dealing with multi-force members, first thing to do is to solve for the reaction forces of the entire structure. So in the previous diagram, I had a roller connection at A, so I have some external force AY, have a pin connection at E, so I have some external forces EX and EY. Using the entire structure, I can solve for those reaction forces. So that's officially the first step. But like we've seen in this class, that's been the first step for a few problems that I haven't actually done that for. Similar situation here, you don't always need to do that. Sometimes you can start other places and then come back and use that as a check of your answer, like you've seen me do, as I said, at least a few times before in this class for various things. The real meat and bones of this is to take my entire structure and I want to break it apart and analyze each member separately. So similar to what we saw for method of joints, I only looked at one individual joint and kind of ignored everything else and only did statics analysis on that one joint. Similar thing here, but instead of looking at the joint, I look at each individual member. So I take that one member, kind of pull it off of the entire structure and analyze that one member by himself, knowing that each time there's a pin connection, that pin connection can support both X and Y forces. And so basically these come from the other part of the structure pulling or pushing on it. So if I want to look at this guy back here, if I look at member ABC, I'm going to take him, pull him apart, and then at joint B, there's going to be some external force that comes from this horizontal member. So this horizontal member can either be pushing or pulling on my original member at pin connection B. And so there'll be some forces, BX and BY, that arise from that. Similarly, at pin C, this other angled member can be either pulling or pushing on member ABC. And so there'll be some kind of external, and again, external to member ABC, forces CX and CY that's come from this other member. And so once I break that guy apart, I can then do statics analysis, use equations of equilibrium on that member. I do the same for each other member. So again, previous situation, there's 3 members there. Break those apart into 3 different structures essentially, and do rigid body analysis on all 3 structures. And that should give me enough equations to solve for all my unknowns. So again, graphically, what I'm doing, taking this structure here and breaking it apart so each member will become its own free body diagram with all external forces acting on it, as well as pin connection forces that arise from the interactions between members. So again, I have ABC over here. At pin B, I have some forces BX and BY that come from this member over here that has equal and opposite forces BX and BY. So easiest way to have equal and opposite forces is just draw them in the opposite direction. So for this member ABC, I drew BX to the left, BY going up. So I'm essentially assuming that this horizontal member is pushing him to the left and pulling him up, which means that equal and opposite, this angled member ABC is pulling down and pushing to the right this horizontal member BD. So equal and opposite forces at pin B between these 2 members. Similarly, at joint C, I have equal and opposite members, or equal and opposite forces between the 2 members. So whatever ABC is doing to CDE, equal and opposite CDE is doing to ABC. And then similarly for all the other ones, D as well, between these 2 members, equal and opposite forces at each pin. So essentially turned my previous diagram into this, and then this here. Again, I have my AY reaction force, EY, EX reaction forces, external forces, P and F. I can do rigid body equilibrium, so 3 equations essentially, either force in the X, force in the Y, and some moment, or take more than 1 moment. Doesn't really matter how you do it, as usual. Obviously, some ways are going to be easier than others, as we've seen, but I have 3 equations for this member. I have 3 equations for that member, and 3 equations for that member. Gives me a grand total of 9 equations if I need them. A lot of times you won't need that many. For example, in this case, I have technically only 6 unknowns, BX and BY, CX and CY, DX and DY. Once I have those, it's just equal and opposite everywhere else. So only need 6 equations, but I have up to 9 if I need them. So certain situations, you will need more, but you'll never need more than what you have. So again, here, I can get up to 9, only need 6. That's fairly common. Maybe there'll be something else where maybe I don't know this force and I'll need a 7th one, but that's fine because I have up to 9. Some terminology. A multi-force member or structure is non-rigid or collapsible if, when you take the supports away, it basically falls over, or if it is able to move. So if I have a structure like this, supported by a pin and a roller, have some forces on it, and at this point it's in equilibrium. If I take those supports away and it's no longer in equilibrium, this thing can actually collapse. So in this case, be like scissors. If I'm pushing that guy inwards, pushing that guy downwards, this is going to move inwards, that guy's going to move inwards, and basically it's going to turn into basically straight line, up and down. So this is a non-rigid or collapsible structure. On the other hand, if I take the supports away and it doesn't collapse or doesn't move, that is a rigid structure. So again, if I put a cross member in here to the similar scenario I had before, still pushing down, still pushing to the left, because I have this cross member, that's going to stop this thing from moving inwards. So non-collapsible rigid structure in that case. So that brings us to frames and simple machines. So frames and simple machines are usually connected by pin connections. And if I remove the stipulation that we've been working with the past week or two about these forces that need to be applied just purely at the joints, so now I can apply a force anywhere I want. Now I essentially have a frame. A similar scenario is a machine. So machines used to design or transmit forces. So machines are generally moving structures. Frames are essentially stationary structures, but they are composed of these multi-force members that are all pin connected. And so I can assign the forces acting at the joints and supports by using equations of equilibrium. So kind of the procedure we saw before. Take this frame or machine, whatever it is, break it apart into its different members, and then I can solve for those internal forces, Bx, By, Cx, and Cy, using the equations of equilibrium. So that gives me the forces acting at all the joints. You can always find the forces at the supports using the free body diagram and rigid body equilibrium on the entire structure. So again, this follows kind of what we described before, using the multi-force members. And so officially, the procedure, you want to draw the free body diagram for the entire structure and solve for any support reactions. This is if you can. So again, like we saw in the previous kind of example, I had 6 unknowns, 9 equations. I had a pin and a roller connection. If instead of having a pin and a roller, I had 2 pins, for example, that's going to give me an extra external reaction force that I wouldn't be able to solve for using standard rigid body equilibrium. But now in this situation, that's only 1 more unknown. So instead of having 6 unknowns, that gives me 7 unknowns. I still have 9 equations. So I can actually solve for that. So here's a situation where I have a structure that looks statically indeterminate, but ends up being statically determinate if it's one of these multi-force members that's all pin connected. So if you can solve for your reaction forces, if there's 3 or less, you can go ahead and do that first. If not, that's fine too. You can solve for some of them if you can. Then you can break the structure apart into its component members and draw free body diagrams for those, and then apply rigid body equilibrium to any of those to solve for either external or internal pin connections. So at each pin, you'll have internal reaction forces coming from the other members of the structure. So external to that one structure in the X and Y directions. Then again, you have a certain number of unknowns, a certain number of equations, essentially 3 for each member in 2 dimensions. And so write down as many equations as you need to solve for as many unknowns as you have, and then basically just solve those equations for each unknown. So that is the procedure for multi-force members and frames and machines. So we'll see some examples of those later today in class.